Now continuing with optical isomerism only, that is we will calculate the specific rotation. That is specific rotation. I have already said you earlier also, the specific rotation is denoted with the letter that is alpha, which is equal to theta by c into L, where alpha is the degree of specific rotation, theta is the angle of specific rotation. We can say that. Now next is theta is the angle of specific rotation, c is the concentration, L is the length of the decimeter tube, got it, which is taken to be as 1 decimeter. We can say that, clear. Now the specific rotation also depends upon the temperature and wavelength of the light it is used. Listen carefully, the specific rotation, it is not there in the formula, this is the note, you can write it down. The specific rotation depends upon the temperature and the wavelength of the light used, which light you are using it, whether yellow light or green light or blue light, which light you are using it, and it depends upon the temperature also, we can say that. So hence for that particular purpose what we find is that, now you may ask me that how it depends upon the temperature. Generally what we find is that, suppose if I increase the temperature, what will happen? If I increase the temperature, the concentration, you know, it is nothing but the concentration, generally concentration expressed in terms of molarity. Got it? So if you increase the temperature, the concentration is going to increase because volume is going to decrease. How? Concentration means molarity is equal to nothing but weight by molecular weight into volume in liters. Got it? Volume in liters, we can say that. So volume, the solution is going to decrease because on heating the solvent will evaporate. Got it? So the volume is decreased means concentration is going to increase. We can say that. So generally the reaction is being carried. Reactions means this particular experiment is being carried at room temperature. We can say that, which is considered to be as 25 degrees Celsius or 298 Kelvin. Remember it, 25 degrees Celsius or 298 Kelvin. And here the standard light which you are using is nothing but the light of the sodium vapor lamp. Sodium vapor lamp, which is a yellow light, we can say that. Got it? It is considered that the sodium vapor lamp which gives out the wavelength of the light, that is considered to be as the yellow light, and that is the standard light we are using it. Got it? Whose wavelength is around 5896 centimeter. We can say that. 5896. We can say that. 5896 centimeter, I said nanometer. I'm very sorry, it is not measured in centimeter, it is measured in nanometer. The wavelength of the light. This is the wavelength of the yellow light, that is a sodium vapor lamp from which we are getting the light. Alright, clear, it is known as. So in this way, this we are taking it. This how we measure it. That is the angle of specific, this is nothing but the specific rotation, and this is called as the angle of specific rotation, we can say that. Clear? We measure it. Whichever is unknown, we can find it out. Next, after that, one more thing you listen here. This optical isomerism, it comes under what? Stereoisomers. So we are having a chiral center. I have said you already about it. Chiral center. So we are also having a stereo center. Now what is the difference between chiral center and stereo center? You noted one particular point, that all chiral centers are stereogenic centers, but all stereogenic centers are not chiral centers. I'm going to repeat. All chiral centers are stereogenic centers. All chiral centers are stereogenic centers, but all stereogenic centers are not chiral centers. All stereogenic centers are not chiral centers. What do you mean? Now, under stereoisomers, are we having only optical isomerism? No, we are also having geometrical isomerism. So, this particular carbon is what? It is a stereo center. This particular carbon is what? It is a stereo center. But this particular carbon is what? When it is attached to 4 different atoms or groups, it is known as chiral center. This is 2 years. Understood now? Now, this particular chiral center comes under stereochemistry. It comes under stereoisomerism. So, all chiral centers are stereo centers. But all stereo centers, this particular stereo center, is it a chiral center? No. I think you got it now. Isn't it? This is nothing but cis and trans. AA and BB. We can say this is your cis. So, this is your chiral centers. So, here the chiral centers, we can say that it is tetrahedral in nature. And here the chiral centers is trigonal planar. Because you can see the bond angle is how much? I said you already. 120 degree. We can say that bond angle is. And here the bond angle is 109.5 degree, and more about it you will study in chemical bonding when I will teach you. Alright, so in this way it is trigonal planar, this is tetrahedral in nature, we can say that. So understood this particular point, that all chiral centers are stereo centers, but all stereo centers are not chiral centers, so to say. Alright, this particular point. Fine. Now, next is, after that we'll come to, that is how to represent the three-dimensional molecule. Alright, representation of three-dimensional molecule. There are different methods of representation of three-dimensional molecule. Different methods are there. One is known as the flying wedge representation. Flying wedge. Another is known as the Fisher projection. Fisher, I am writing on the board, just let me rub my specs. Yeah. The flying wedge representation. What I said you? Flying wedge representation. Or three-dimensional, this one is. Flying wedge representation or three-dimensional representation. Now, what is flying wedge representation? See here. For example, let us say this is H, OH, and we are having let us say this one is what is that? I'll write CH3 and I'll make this one dark, this one. Let us say this one is COOH. Fine. This is known as flying wedge representation. Let us say. Now, how do we represent now this is three-dimensional, you can see it. Now, how do you represent it? When I am writing this three-dimensional, two-dimensional plane, how do I represent it? I consider that this two, that is what you can say H and OH group, it is on the plane of paper. On the plane of paper. Like you can see, this is a board, two-dimensional, so it is on the plane of paper or on the plane of board, we can say that. Now, this particular one, which is known as the wedge, alright, and the other one is known as the dash. Alright, we say one is the wedge, another is the dash. Now, this particular one is below the plane of paper. This particular one below. Below means here I can say it is inside. This CH3 group is inside the board, inside it is. And this is what you can say above, outside. It is above, COH. So this one is above. This group is above the plane of paper. Alright. So in this way, this is wedge, dash, clear. What you find is that this particular one is above the plane of paper. So you can remember this way, the dark one, the solid line is above the plane of paper. This particular one, this lines, we can say that, got a dash, we can say, it is below the plane of paper, means it is inside the board, and this is outside, and this is on the plane of paper, means this is on the plane, on the board, we can say that. These two are on the board. So when I draw it in this way, these two are on the board. When I draw it in this way, this is below, inside, and this one is outside. So this is your three-dimensional representation. This is called as flying wedge representation. It is said to be as, okay, flying wedge representation. Okay, understood now? Next, after that we are having Fisher projections. Fisher. A scientist was there whose name was Emil Fisher. He gave us also, later on I will teach you, the RS system of nomenclature. Capital R, capital S. R means rectus and S means sinistus. What I said? R means rectus, R-E-C-T-U-S, rectus, and S means sinistus, S-I-N-U-S, sinis, S-I-N-I-S-T-U-S, sinistus. What do you mean by that? Rectus and sinistus. Rectus means when it rotates the plane of polarized light towards right, and sinistus means when it rotates towards left. But how it does, all these things in details I will tell you later on in this chapter. When I will come, I will tell you about it. Now let me go to the Fisher projections. Fisher, F-I-S-C-H-E-R, Fisher projection. We can say Fisher projection formula. Now the same formula I am writing in this way. This is Fisher projections. Alright, so here what will I do is that here that is COH, I will keep it. Here that is CH3 group, I will keep it. Here it is H and OH. Generally, listen carefully. Now this is a carbon atom is considered. This is considered as the carbon atom. We can say that. This one is considered as a carbon atom. This line, bond line, is considered a carbon atom. We are not showing it, but it is considered as a carbon atom in Fisher projections. Generally, listen. You have done it, what you can say, secondary prefix, you have done it. You have done in the secondary prefix, you have arranged in the preferential series, you have arranged it. So the one which is having, listen carefully, the one which is having the higher oxidation state, that is placed at the top of the Fisher projection formula. That is placed at the top in the Fisher projections formula, we can say that. The one which is highly oxidized, alright. And this is your longest carbon chain is kept. That longest carbon chain is always kept vertically. Longest carbon chain means you will say here carbon is there. Here carbon is there. No. The one which is having the carbon atom, I will place it vertically. Listen carefully all of you. The carbon atom, see carbon, carbon, carbon. Longest carbon, 3 carbon. So I placed it vertically. So always the longest carbon chain should be vertical. Got it? And the one which is having highly oxidized means the one which is higher in the preferential series. For that reason I said you have to remember the preferential series. So this should be kept at the top. Will be at the top. Okay? That's it. You have to remember. This much you have to remember the Fisher projections. You have to write it in this way. Alright. The way I have written it, just draw 4 lines. Suppose you will say, sir, one more is there. Okay, no problem. One more line you will write in this way. One more carbon atom. Like suppose here Br is there and here Cl is there. And here that is CH3. No problem. This is another carbon. You can write in this way. No problem at all. Alright. In this way you will be writing it out. The one which is having the maximum number of carbon which will be placed vertically, and the one which is having the high oxidized state means higher in the preferential series, that will be placed at the top. We can say that. And rest you will place it accordingly. We can say that. So this is your Fisher projection formula, we can say that. This is one way of representation, the Fisher projection formula. Alright, but Emil Fisher gave us the RS system of nomenclature that we'll study later on. RS system of nomenclature. Next is your sawhorse. Sawhorse, and another will be a Newman. So sawhorse, what I said? Sawhorse. That is projection. Sawhorse, we can say that. Formula or sawhorse projection, whatever you can say that. You can say sawhorse formula also you can say, or sawhorse projection also we can say that. Now here in case of sawhorse we are having 2 types of projection or 2 types of formula we are having. One is your staggered, another is your eclipsed, we can say that. Now what is staggered and eclipsed? In staggered, that is the groups will be anti-parallel to each other. Listen carefully. In staggered, the groups will be anti-parallel to each other. That is the bond angle between them will be 180 degree. Anti-parallel. In eclipsed, it will be parallel to each other. That is the bond angle between them will be 0 degree. Alright, what I said? One will be staggered. Now you can see it here. I am drawing one line in this way. This is carbon atom, this is carbon atom. Let us say this is group A and group A. See here, it is anti-parallel. See. And here it is, if it is in this way, the B's, then this B will be anti-parallel in this way. If suppose the C, let us say I will be drawing the C in this way, let us say this is your C, then this C will be in this way. That's it. So this is known as anti-parallel, or this is called as staggered. Staggered configuration, we can say that. Clear? So it is staggered where the bond angle between them is 180 degree. See, this A and this A, bond angle is 180 degree. Now, this one C and C, this B and B, we can see they are anti-parallel. But what is eclipsed? What is eclipsed then? Now, if this is your A, this is also your A, this is A, this is A. See, parallel, they are parallel. Bond angle between them is 0 degree. Between 2 parallel lines, what is the bond angle? 0 degree. Now, this is your B, and this is also is B. Alright? Now, this is your C, then this is also is C. Finished. These two are the carbon atoms and they are the any group, we can say that. Clear? In this way, what we find is that in case of eclipse, the bond angle between them is, between them, this A and this A is how much? Let us say, mark it as 1 and 2. Let us mark it as 1 and 2 here. First carbon, second carbon. Let us see. So, between 1A and 2A, bond angle is 0 degree. Here between 1, where is that A? 1A and 2A, the bond angle is 180 degree. Got it now? This is your nothing but known as, what is that? Sawhorse representation, we can say that. Thank you very much.